In this video, we're going to look at surface gravity waves again, and we're going to look at this distinction between what would be called deep water waves and shallow water waves. The distinction will depend on whether the depth of the ocean relative to the wavelength is either a big number or a small number. So if the ocean is very, very deep relative to the wavelength of the waves we're considering, then that would be called deep water waves. On the other hand, if the wavelengths are very long compared to the depth of the ocean, then we're going to be in the shallow water limit. So I want to illustrate this in with the numerical model that we've been running. And so over here, I modified the previous code a little bit by changing the size of the domain. So here we have the length L for the width of the domain to be 1,000 kilometers, and the depth to be very deep to be 15 kilometers in this case. And we have, we're going to put a hump of water, which is down here in the initial condition. I have both parts of the code showing at once, to be in the form of a bell-shaped curve whose width, what we call the standard deviation, or the width, is roughly 2 sigma, whereas sigma is about 14 kilometers. So the width of the hump is roughly 25 kilometers or so. So there's going to be a hump of water 25 kilometers wide, which will start with an ocean at rest, and then we'll let that adjust under the action of gravity. And we're going to do it first in the case where the depth is 15 kilometers. So if I run the code down here, I illustrate the distinction between what the hyperbolic tangent of k times h will be for that dispersion, for that wave or hump. And what we get is the hyperbolic tangent is very close to 1. And so that's going to be the limit of deep water. And you see here you get the hump broke down in a bunch of waves, and all the waves dispersed away, or they propagate, and the longer waves seem to move faster than a shorter wave, but the packet disperses away. Alright, so this is the first example. Now we're going to go to another case where we're going to make the depth of the ocean more realistic. So I'm going to go to a depth of, let's say, 3 kilometers, and we're going to do the same initial condition. Everything else will be the same. Okay. Clear all. And now we see something very different. As the packet breaks up, it breaks into 2 humps which propagate away with very little or no dispersion. And in this case, if you compare KH to the hyperbolic tangent, they're almost equal to each other. So that's very close to the shallow water limit. It's not quite, there's still a little bit of dispersion. So if we make the ocean a little bit shallower, let's make it 1 kilometer. Clear all. And now these are very close. The first 2 digits are equal to each other. The difference is less than 1%, and there's very little dispersion now. 2 humps propagate away. Remember, it's a periodic domain, so 1 humps come back in, and you'll see when they interact with each other, there'll be constructive interference, and we'll get back the big hump, but the 2 waves will just pass through each other with no other interaction. That's because we're studying the waves in the linear limit where there's no interaction. Alright, so these are very distinct behaviors. One case where the waves of different wavelengths propagate at different speeds. So the initial packet, which is that Gaussian, that bell-shaped hump of water, that packet breaks apart into many waves that travel at different speed, and the packet disperses. That's in the deep water limit. And now we have the other limit, which is the shallow water limit, where there is no dispersion.